Welcome back, students. In this lecture, we are going to apply some of the things that we've been talking about thermodynamics to chemical reactions in a field that we could call thermochemistry. So what we're going to be looking at today is how thermodynamics operate in chemical reactions. The learning goals for today are going to be to describe how breaking and making chemical bonds changes the internal energy and the enthalpy of a system. Energy is stored in the bonds, so if we break those bonds or make bonds, we change the other degrees of freedom, the other energies the system has, which is going to be reflected in something like a temperature change. We're going to want to be able to calculate the change in enthalpy for some reactions. We have some definitions here that we'll talk about. We have formation reactions, and then this just refers to any generic reaction. And these are going to be important for determining the enthalpy of any chemical reaction. We'll talk about how to calculate the enthalpy at temperatures other than the standard temperature of 298.15. And at the end, we'll talk about how calorimeters experimentally determine the change in internal energy and the change in enthalpy. And this will be our second lab. We'll go through one of these experiments. Let's start by thinking about what a chemical bond is. Last semester, we saw that if we had a stable chemical bond, that stably bonded molecule was lower in energy than the two separate atoms. So we talked about the hydrogen molecule and saw that putting 2 electrons in the H2 molecule was lower in energy than putting 1 electron each in 2 hydrogen atoms. So what does this mean? What it means is that if we have a system where we have a reaction, so say we have a reaction from 2 atoms becoming 1 molecule, we have lost energy. So the 2 atoms were at 1 energy, they form a molecule that's at lower energy, and the energy is now been lost since we went to lower energy. What has happened to this system? Well, the energy has had to have gone somewhere. It must either be stored in the system or released to the surroundings. In other words, we should be able to harvest the energy stored in these 2 isolated atoms as they form their molecule as work. So we can't harvest all of this energy, and the stuff that we can't harvest would be lost as heat. This might sound a little bit weird saying there's energy stored in isolated atoms, but it makes more sense when we think about molecules. So some relevant examples of this are going to be energy stored in the carbon-carbon and carbon-hydrogen bonds of chemicals like octane and glucose that is released upon their combustion to carbon dioxide and water, either in a combustion engine like our car or in ourselves as we breathe and live. Another example would be energy stored in the phosphoanhydride bond or the mixed anhydride bonds of molecules like ATP or glyceraldehyde-free phosphate that's released upon hydrolysis. So chemical bonds can store energy. As we break that energy, as we break those bonds, energy comes out, and that energy can be harvested into work. And we'll look more about how that energy is harvested into work in the next lecture. Today, we're just going to talk about the process of chemical reactions. So there's some general things we want to discuss. First, if we were to break a bond, that typically requires energy because bonds are stable, otherwise they wouldn't form. And when we make a bond, that produces energy. In a chemical reaction, bonds are broken and then made. If that chemical reaction releases energy, that means you get more energy out of making the bonds than you do for breaking the bonds. So you produce more energy when the bonds are formed than it took to break them. And what you have, so examples of this like we just discussed were combustion of hydrocarbons. So there's more energy in the CC and CH bonds than in the CO and HO bonds. So as we break the CC bonds, it doesn't take that much energy, but when we make the CO or HO bonds, that releases a whole bunch of energy. And so we get more energy than it took to break that bond. How can we talk about a chemical reaction? Well, every bond itself has an enthalpy associated with it. And you may remember from previous chemistry classes talking about things like bond enthalpy. So this is a table from the book that talks about the different types of bonds. So you have the keys here. So we have single bonds, double bonds, triple bonds with self, and then bonds with hydrogen and carbon and so forth. And you can see that there's all this different variety of bond energies or enthalpies. If we want to know how a process occurs, we can simply add up the number of molecules broken and formed. So let's look at this example here. We have the formation of ammonia. Now, how do we form ammonia? Well, we have to break apart nitrogen and hydrogen atoms in order to make NH3 molecules. So how does this happen? It doesn't really matter how this happens because enthalpy is a state function. So we don't need to know the actual mechanism by which nitrogen and hydrogen combine to form ammonia. We can simply say, well, let's imagine that I'm breaking these things apart one step at a time and then piecing them back together. So here, in this case, we talk about the bond enthalpy from going from a nitrogen molecule and hydrogen molecules into isolated nitrogen and hydrogen atoms. And then one step at a time, we form one NH bond, two NH bonds, and three NH bonds until we have ammonia. And in theory, this process would be able to predict the enthalpy for any chemical reaction. Now, there's a problem, and hopefully you'll be able to see this problem here, is that these enthalpies for making and breaking bonds are very large compared to the overall relatively small change in enthalpy for this process. So here we have steps that are on the order of, say, 400 kilojoules per mole in terms of breaking and making these bonds. But the overall delta H for this process is about 40 kilojoules per mole. So it might not be apparent to you that this would be a problem, but if we think about this, say we have an error in this 400 kilojoules per mole of about 4 kilojoules per mole. Now, that's pretty good. That's an error of 1%. If you got that in any one of your chemistry labs, you'd be pretty pleased with yourself to get an error of 1%. But if we get that 3 times, so we have 4, 4, 4, now what we have at the end of this, that error accumulates and we have something that's 45 plus or minus 12. Now that all of a sudden is a very large error. So this is not the best way to go about this process and trying to figure out the enthalpies of these reactions. We'll talk about what that best way is on the next couple slides. In the above description of chemical reactions that we just did, we have been talking about the enthalpy instead of internal energy. And you'll be familiar with this from previous chemistry classes. We always talk about enthalpy and not internal energy. Internal energy is this new weird thing we brought up in thermodynamics. And why have we done this? Remember that the internal energy is more natural to use when considering constant volume processes, while enthalpies are more natural for constant pressure processes. Most chemical reactions are occurring at constant pressure, that is the atmospheric pressure that they are exposed to on the benchtop or in the hood, meaning enthalpy is typically a more straightforward measure. So the heat of any process is directly related to that enthalpy if it's happening at constant pressure. A lot of processes that we do in chemistry are actually isobaric and isochoric, so they have no change in pressure and no change in volume. And in those sorts of cases, the enthalpy and the internal energy are the exact same. So if we have no change in volume or pressure, there's no difference between the internal energy and the enthalpy. There are some branches of chemistry that work with gases, and those would more often use internal energy than enthalpy. But for us doing solid-liquid reactions, we typically use enthalpy. There's 2 types of chemical reactions that we're familiar with from previous classes, and those are exothermic and endothermic reactions. So exothermic reactions have heat flow out of the reaction, and they have a negative delta H. And endothermic reactions have heat flowing into the reaction, and they have a positive delta H. When we're talking about reactions, we have a couple of different definitions that we'll want to work with. The first one we'll look at is the enthalpy of a reaction. So this is here is we have delta for delta H, and then we have this little R subscript in there that's just saying this is an enthalpy of a chemical reaction. So that reminds us that we're talking about a chemical reaction. This is the heat exchange between the system and the surroundings as the reactants are transformed into products at conditions of constant pressure and temperature. We'll also have standard enthalpies of reactions, and these are what you're going to be more commonly familiar with. The standard enthalpy of a reaction, we have this little degree symbol here, and that indicates a specific pressure and temperature. So for us, we're going to have a pressure of 1 bar, so a normal atmospheric pressure, 298.15 Kelvin room temperature, and 1 mole of product form. So this is a standard enthalpy of a reaction. Now, you may have wondered something maybe in this discussion or maybe for your whole chemistry career, that how can we actually do this? So you have done, I assume, a fair amount of chemical reactions in your time here at Hillsdale and probably before. And what you have probably noticed is that chemical reactions do not remain at the temperature you start them. So if we started our reaction at 298.15 Kelvin, at the end of the reaction, maybe you had to boil it, maybe it lit on fire, but it's certainly much hotter, or in some rare cases colder, than how we started. So how can we have this standard enthalpy of a reaction where we have the same temperature at the beginning and end? The key to understanding this is to remember that enthalpy is, in fact, a state function. So our process would be our reactants at 298 being converted to our products. For most reactions, this would end up being at a higher temperature than 298. So we have hot products, but then we can allow the products to cool back to 298. Since enthalpy is a state function, the fact that we had this intermediate where we had hot products doesn't actually enter into the calculations at all. And we can calculate a standard enthalpy of a reaction at constant temperature because the beginning and ending states all have the same temperature. Now, we're going to go into a very specific kind of enthalpy here next, and we'll go to the slides to investigate this. And this is a standard enthalpy of formation. So the symbol we use is the same as for a reaction, but we put an F here in place of the R to denote that we are talking about a very specific type of reaction, a formation reaction. So a formation reaction is a reaction where the only product is 1 mole of the species of interest that we're talking about, and the only reactants are pure elements in their most stable form under standard conditions, and that's the degree there. So when we have a standard enthalpy of formation, this is the enthalpy associated with a reaction, where that reaction is a formation reaction. So let's go over to the board here and look at what this kind of reaction might be. Here I have drawn the chemical formula for acetic acid, and we're going to want to describe the formation reaction for acetic acid. Note that I have the liquid here because the state of matter is very important. The enthalpy of processes is different because the energetics of solids is very different than the energetics of liquids and gases and so forth. So we do have to specify the state of matter. What elements in their most stable state form acetic acid? In this case, acetic acid is made up of carbon, hydrogen, and oxygen. So we simply add carbon, hydrogen, and oxygen. So to form acetic acid, we would need 2 carbon atoms, and carbon is a solid, plus 2 hydrogen molecules, where hydrogen is a gas, and then a single oxygen molecule. And if we do this, this is the formation reaction for acetic acid. So this would have an enthalpy associated with it. It would be a delta FH naught, and I'll put acetic acid here in parentheses, so we're reminded that it's acetic acid. And if we wanted to be extra good, we could say that it is liquid acetic acid. This is the enthalpy of this process is the enthalpy of formation of liquid acetic acid. Now, in doing this, you might have some red flags going off in your mind. You might say, well, how in the world could we do this? How could we take carbon, so graphite, hydrogen gas, oxygen gas, combine them together and get exclusively 1 mole of acetic acid? Why wouldn't we make methanol, ethanol, acetone, water, methane, carbon dioxide, or any other organic compound made up of carbons, hydrogens, and oxygens? Why would we be able to do this? And as I told my students in the past, is not even Dr. Mayette or Dr. Barron could do this chemical reaction. Even the best organic chemists couldn't do this. This reaction is not possible. So how do we find the delta H of formation? And if we look in our big tables in the back of our books, you'll note that every chemical is listed with a delta H naught of formation. So if we can't actually form these chemicals from their elements, how do we come across this number, and why do we list it in the book? What we need to do is come up with reactions that we can actually measure. And there's one really good example of a kind of reaction that always yields the same products, and those are combustion reactions. So combustion reactions start often with hydrocarbons, but really with anything. So they start with some compound, you add oxygen, and what they make at the end of that reaction is that compound completely oxidized. So if we do a series of combustion reactions that we can measure, can we get this reaction here? Let's go through an example of this. So we'll start with a chemical reaction that's going to look funny to you. So I'll start by saying we have 2 water molecules plus 2 carbon dioxide molecules forming 2 oxygen molecules, and our liquid acetic acid. Now you might look at this and go, okay, this is still a reaction that we're not going to be able to do. But note what this is simply the backwards version of a combustion reaction. So if I take acetic acid and I take oxygen and combust those, I will get carbon dioxide and water. So this reaction here is simply the reverse of the combustion reaction. Therefore, the enthalpy of this process, I'll write delta C for a combustion reaction of H naught, is simply the combustion of our liquid acetic acid. Now, it's also the negative combustion of liquid acetic acid because I have the opposite here. So if combusting acetic acid releases 100 kilojoules of energy, then doing the opposite process would gain 100 kilojoules of energy. So we just put that -1 there. Now let's go through another combustion process. I'll come down here and I will write another combustion reaction where we have 2 hydrogen molecules plus an oxygen molecule forming liquid water. So here we have another combustion reaction. And this reaction would also have an enthalpy associated with it. Note that I could actually do this reaction. I could have hydrogen and oxygen and combust them and get water only. So this here would have an enthalpy of this reaction. It would be a combustion reaction of forming liquid water. In this process, we have 2 molecules of liquid water where we actually only want 1. So what I'm going to do is divide this all by 2 and put a big 2 here on the outside for us. So I have 2 hydrogens, 1/2 oxygen, and then 1 water. So what is the enthalpy of this process? Well, when I've written it out in this way, it's obvious. This is the formation reaction for liquid water. So I'm going to erase the C and put an F there to remind us this is in fact a formation reaction. And since I'm doing this reaction twice to make 2 molecules of liquid water, I need to double this formation reaction here. The last thing we'll do is combust carbon. So we'll have an atom of carbon, a molecule of oxygen, and we'll combust that to make carbon dioxide. And in order to get a balanced reaction, we'll need to do this twice. Just like above here, we have 2 times the formation of our solid or our gaseous carbon dioxide. So I've done this, and what have I ended up with? Let's sum this chemical reaction. So just like any other sort of math, we can sum up chemical reactions. If something appears on both the product and the reactant side, we can cancel it out. So here we have 2 carbon dioxides, and we have 2 carbon dioxides from this bottom reaction. So we can cancel out both of these carbon dioxides. Here we have 2 H2Os, and we have 2 H2Os here, so we can cancel out those 2 H2Os. Here we have 2 oxygens, and on this side we have 1 oxygen plus 2 oxygens, so we can cancel out these 2 oxygens here, and I'll cancel out these 2 on the bottom, leaving us with 1. What do we have at the end of this reaction then? We have simply 2 hydrogen molecules, so I'll write 2 H2 plus 1 oxygen molecule plus 2 carbon atoms, and then on the product side, all we have is C2H4O2. So in considering these 3 combustion reactions, 2 of which are actually formation reactions, we have described the process by which you would add hydrogen, oxygen, and carbon together to get only liquid acetic acid. And the enthalpy for this process down here, which is the enthalpy of formation of liquid acetic acid, is simply the sum of all of these enthalpies here. So I'll write it in this way. I'll write that delta formation H naught C2H4O2, so liquid acetic acid, is equal to the negative delta C, so the delta combustion of our liquid acetic acid, plus 2 times the enthalpy of formation of liquid water, plus 2 times the enthalpy of formation of gaseous carbon dioxide. I would be able to put all of these numbers together, since they are combustion reactions that I can measure, to determine the delta H naught of formation of this acetic acid, even though that is not a reaction that I can do. This is a form of Hess's law, and Hess's law tells us that I could add any reactions together and add their enthalpies together to get the enthalpy for some new reaction at the end of the day. I'm going to rearrange this here to get it into the more common version that we usually express Hess's law in. And so that's going to be considering the combustion reaction. So I can say that the delta of combustion of my liquid acetic acid is equal to the following. It's equal to 2 times the delta H naught of formation of liquid water plus 2 times the delta H naught of formation of gaseous carbon dioxide minus the delta H naught formation of liquid acetic acid. Now, I've just rearranged this, so I simply added this to this side and then subtracted this over to this side to get this expression. And what you'll note is that if I had this combustion reaction, what would this combustion reaction look like? I have it up here. So this combustion reaction is simply C2H4O2 plus 2O2 gas yields 2H2O liquid plus 2CO2 gas. In other words, I'm saying that the enthalpy of this reaction is equal to the enthalpy of the formation of this guy, the enthalpy of formation of this guy, and then subtracted the enthalpy of formation of this guy. So we're doing the products minus reactants that you may remember from Gen Chem. I have neglected oxygen in here. Why have I done that? I've done that simply because the enthalpy of formation of oxygen is 0. Why is that? Recall that the enthalpy of formation of a chemical is the reaction in which O2 is the chemical I'm interested in, and the only products are the elements in their standard state, which is O2. This is obviously no reaction here. So the enthalpy of this process is going to be 0. There is no difference between O2 and O2. We can write this in the following way. We'll say that in general, the delta H naught of a reaction is equal to the following. It's equal to the sum over I, where I is all of the chemical reactions or elements here, and we have new delta H naught formation of all of our substances. So here we're simply summing over all of our enthalpies of formations. This nu is the stoichiometric coefficient. It's positive for products and negative for reactants. So in the above example, nu H2O is equal to 2, nu CO2 is equal to 2, and nu acetic acid is equal to -1. And technically we have nu of O2, and that's also equal to -2. Although since the delta H naught formation is O2, we don't see that in the above reaction. At some point, we may want to know the enthalpy of a reaction at a different temperature other than 298.15 Kelvin. How would we go about calculating this? Essentially, what we're going to do is recall our definition of enthalpy. So we calculate our enthalpy by saying that the change in enthalpy is equal to the integral of the heat capacity dt. So if we were trying to figure out our enthalpy at a different temperature, what we could do is the following. If we knew our enthalpy at 298.15, we could say, well, what's the enthalpy at some different temperature? And what we'll do is say that the enthalpy at some different temperature is equal to the enthalpy at 298.15 plus the integral of Cp dt from 298.15 to whatever new temperature we are trying to get at. How we'll do this for a chemical reaction then is the following. So this is just for any given chemical. For a chemical reaction, we would say that delta H naught reaction at some new temperature T is equal to the delta H naught reaction at 298.15 that we would get just like we did before, looking at these numbers in the book, adding all the delta H to formation together, plus the integral from 298.15 to whatever the temperature is of delta Cp dt. Delta Cp may or may not be a function of temperature depending on the reaction at hand. What is delta Cp? We'll derive this in class. Essentially, delta Cp is the same thing that our delta H naught reaction is. So delta Cp is simply the sum of all of the individual heat capacities multiplied by their stoichiometric coefficients. Again, with products being positive and reactants being negative. And so we'll show how we can prove this in class. The last question we'll go over today is how do we actually experimentally measure the change in internal energy and enthalpy? We'll use a setup shown here called a bomb calorimeter, and we'll actually do this in lab 2. The way bomb calorimeters work is we add a small sample of a combustible material into a rigid vessel, as shown here, and pump it full of oxygen. We'll then ignite the sample using electricity, which will combust the sample and release energy. This is a rigid container and it's made of steel or some other hard metal, so the volume is constant. When we have a constant volume, that heat of the process is going to be related to the internal energy rather than the enthalpy. The energy released in this process causes the temperature of this water bath that's surrounding our vessel to increase. This water bath is called the calorimeter. We know the heat capacity of the calorimeter, so as the temperature of the calorimeter is increased that we measure with a thermometer, we can convert that into the heat that must have been released in order to increase the temperature of that calorimeter by the amount that it was increased, which is usually on the order of 1 to 2 degrees Celsius. What we do then is take that heat and we say that heat is directly equal to the internal energy because there's no work done in this process. We convert that to a molar quantity. So we start by, maybe we do a 1 gram sample here, and then we say, well, this is how much heat was released in 1 gram, how much heat is released in 1 mole. We can do that conversion relatively easily. What we do next is convert from delta U to delta H. And we do that in the following way using our definition of enthalpy. Enthalpy was defined as U plus PV, so that means delta H is equal to delta U plus delta PV. It's easy for us to look at it in this way using the ideal gas law that delta PV is equal to delta nRT. We'll approximate the change in enthalpy by saying it's equal to the change in internal energy plus the change in the number of moles of gas specifically times RT. Now, in doing this, you might be angry because I told you in part of this setup that we are, in fact, changing the temperature. So you're saying, well, why aren't we considering the change in temperature? And that's basically because it is small and doesn't really matter relative to the change in the number of moles of gas. And we'll go through an example problem in the homework that shows we don't really need to consider this as relatively low impact in terms of the enthalpy. And all that we need to do is consider the change in the number of moles of gas, as changing the moles of gas will change the pressure, and that's going to account for this delta PV here. So this is how we'll convert from the internal energy change that we measure, because we're measuring heat at constant volume, into a change in enthalpy that we can then report and use maybe to figure out enthalpies of formation. So that is all for thermochemistry here. The conclusions that we want to take away are that we can use enthalpy to describe chemical reactions easier because they usually occur at constant pressure. Since enthalpy is a state function, we can describe a reaction in any way we like, whether or not that's considering bond enthalpies or enthalpies of formation of these reactants and products. It doesn't matter how the reaction actually occurs because it's a state function. So all we need is to have the same initial and final state, and any path that gets there should have the same delta H. And to determine these things experimentally, we use bomb calorimeters, and we're actually going to go through this process in lab 2. So with that, I will talk to you about this in class. Hopefully a lot of this was a review for you guys. If any of it was not, or you're shaky, it's been a while since you've done these things, please ask about it in class, and that's what we'll be doing in this class period.